Humans are going back to the moon with the Artemis missions. Not just to visit, but to eventually stay. And that is incredibly exciting. But scientifically speaking, I don't think the Artemis missions are going to be that useful, at least not directly anyway. Artemis is all about furthering human space exploration and developing a moon base, so it's been funded for political and economical reasons, rather than for answering specific scientific questions about the moon itself. And if you're a scientist, well, that's a big problem, because there are so many things that we still don't know about our nearest neighbour, from how it formed to strange flashes of light and what's actually going on beneath its surface. The kind of things that tell us not just about the moon's history, but the Earth's as well. So in this video, we're going to dive into 5 things that we still don't know about the moon, and crucially, how we'll solve those scientific mysteries, because the Artemis missions most likely won't. Now, let's dive into our moon mysteries and start with, where did the moon's water come from? Because yes, there is water on the moon. It was suspected for a long time. Even the Apollo samples were tested for water back in the 1970s, but no evidence was found. But through the 90s, people began to suspect again that there really was water on the moon. It was just only found in the permanently shadowed, cratered regions on the moon. We now know that to be true thanks to the combined evidence from missions like ISRO's Chandrayaan-1 lander and NASA's Lunar Reconnaissance Orbiter. And in 2023, we finally got a map of where all the water is on the moon's surface thanks to the Stratospheric Observatory for Infrared Astronomy, SOFIA. Now, the Artemis missions will be searching for water around the landing sites near the south pole of the moon, but this isn't scientifically motivated. If you want a permanent base on the moon, you're gonna need life support for your astronauts living there. So if you can find that water on the moon rather than shipping it from Earth with successive launches, that's gonna be a lot more cost effective. So the Artemis missions have been designed to find and use water as a resource on the moon, not to understand where it actually came from. And the big scientific question around this is whether the water actually formed on the moon itself, or whether it was delivered to the moon by impacts with comets and asteroids over billions of years. Now, the key to figuring this out is chemistry, specifically the ratio of water made with pure hydrogen versus deuterium, aka heavy hydrogen. Different sources of water will all leave behind slightly different ratios of pure hydrogen to heavy hydrogen. So if we want to answer this question of where the moon's water came from, then we're going to need a mission that's been designed to take samples of lunar ice from lots of different areas all over the moon, not just from one landing site, and then bring them back to Earth, ideally, so that we can do incredibly precise measurements on them in labs here on Earth. Combining that information with the map of where all the water is, we could then start to piece together, where has the moon's water come from? Has it formed on the surface? Has it been there since the beginning, or was it delivered by comets and asteroids? Unfortunately, there's no planned mission to do this. The Viper mission is the closest we're going to get in upcoming years. It's a rover that will explore the South Pole. It'll find deposits of water and drill sample cores to test for this ratio of pure to heavy hydrogen. But the drill only goes about 1 meter or so under the surface, and the rover will only rove about 1 kilometer or so, and the tests will be done like in situ on the moon with a lot less precision than we can do in labs here on Earth. Viper is set to land on the moon in late 2027. And hopefully then we'll get the first tentative answers to this question of where the moon's water came from. Next up on our list of mysteries is what causes the bright flashes of transient lunar phenomena, or TLPs. These are very brief flashes or colour changes that occur on the moon's surface that can last anywhere from a few seconds to up to a few hours. And they're not a recent thing either. They've been reported for centuries and we still don't understand them. They are completely unpredictable, and while sometimes they have been seen by multiple observers in different parts of the world, oftentimes it's very difficult to confirm reports that they've actually happened. So what could be causing them? Well, one of the leading ideas is that they're just caused by lunar dust that just happens to be floating above the moon's surface that scatters light in a way that creates these flashes or glows. Think of it kind of like a lunar glitter bomb. But it could also be flashes caused by meteorite impacts with the moon's surface, or, they might not even be real things. It could just be like observational effects, just artifacts that we've seen by looking at the moon through telescopes here on Earth. And that's really the issue here. We just don't have consistent, high quality observations of these events. Because despite having spacecraft in orbit around the moon for decades, none have ever seen one of these transient lunar phenomena, these flashes. Now that could in part be due to the fact that these missions are designed to only see a tiny portion of the moon at one time, so that they can take really detailed pictures from orbit. So could the Artemis missions help solve this? No, probably not. Astronauts might happen to catch one of these flashes while they're in orbit around the moon or they're on the surface. But TLPs are so unpredictable and maybe occur like 1 or 2 times a year, so we'd have to get really lucky for that to happen. If we really want to understand these moon flashes, then we're going to need a dedicated mission that continuously monitors the entire moon, which then has a second instrument that enables a really rapid follow-up in great detail of anything that's spotted. The closest we're going to get to that in the near future is ESA's LUMIO mission, the Lunar Meteorite Impact Observer, which will continuously observe the far side of the moon to catalogue all the impacts from tiny meteorites, which we know hit Earth all the time, right? Every day, but they burn up in the atmosphere, so we don't have a really clear view of how many there actually are. LUMIO will record this on the moon, but it doesn't have a secondary instrument to follow up in great detail to confirm, was it actually a meteorite impact? Was it a TLP? Or are these two things the same thing? LUMIO is set to launch in 2027, so maybe we might get some answers then. But for now, transient lunar phenomena remain, as the name suggests, brief, elusive, and as yet, unexplained. Next up on my list of lunar mysteries then is, why did the moon's magnetic field disappear? So we know that today the moon does not have a magnetic field. So unlike Earth, it doesn't have a protective magnetic bubble shielding it from the radiation in space that comes from the sun and distant supernovae. But we also know that the moon used to have a magnetic field. The lunar rock samples from the Apollo missions contain little bits of metal that act like tiny compasses frozen in time to reveal that the moon's magnetic field was much stronger in the past than it is now. So what happened to it? Well, magnetic fields are generated deep inside a planet's core, where it's so hot that metal turns to liquid, in which atoms get separated into their negatively charged electrons and the positively charged nuclei. It's these moving charged particles that generate the magnetic field in what's known as a dynamo. But for the moon, that internal motion seems to have slowed or stopped, shutting down the moon's dynamo and therefore the magnetic field as well. But we still don't know when exactly that happened or why it happened. So could the Artemis program help answer this question? Well, maybe a little actually, but not directly anyway. The Artemis missions will collect new lunar rock samples, which we can test for those same magnetic signatures that were tested in the Apollo samples. But like the Apollo samples, they're only going to come from one specific region on the moon. Instead, ideally what we do is design a robotic mission to actually collect rock samples from lots of different locations evenly distributed around the moon and then return those samples back to Earth for testing. And unsurprisingly, there is no planned future mission to do that. The closest we'll get in the near future is the Lunar Vertex instrument on board IM-3, which is set to be launched later in 2026. It's going to land in a place known as Reiner Gamma, a region with an unexplained high remnant magnetic field on the surface of the moon. But again, that mission is just focused on one specifically weird area of the moon and not on what happened to the moon's overall magnetic field and why it disappeared. Until we figured that out, we can't understand properly how the moon formed and why it's ended up so different to Earth. Speaking of how the moon formed, the next thing on my list is whether the inside of the moon is liquid or solid. Because you might logically assume that from the moon's lack of magnetic field that the inside has got to be completely solid. And that is what the data from the Apollo missions in the late 1960s and 70s showed. Astronauts left earthquake detectors on the moon's surface, seismometers, to see if they could detect moonquakes. On Earth, we can use earthquakes to get a picture of the inside of the Earth from how the earthquake waves travel around the world. So from their different arrival times and detections at different stations around the globe, we can work out whether the material they've passed through is liquid or solid and where the boundaries are. And thanks to the Apollo missions, we could do something similar on the moon. The data showed that the moon has a crust and a mostly solid mantle of rock underneath that, and then a small metal core. But there were only a few landing sites from Apollo where the seismometers were left, with none on the far side of the moon. So the data was pretty limited in what it could tell us, and now the seismometers have been shut down since 1977. But a big change came in 2011 when NASA's Gravity Recovery and Interior Laboratory mission, or GRAIL, used 2 spacecraft in orbit around the moon to record the ever so slight differences in the pull of the moon's gravity from different areas above its surface, essentially mapping out the moon's structure in more detail. And unlike the Apollo data, it showed evidence for a liquid layer near the boundary between the moon's core and mantle. So can the Artemis missions help us figure out if the moon is solid or liquid inside? Maybe a little bit. The Artemis missions will set up what's known as the South Pole Seismic Station, the SPSS, putting a moonquake sensor on the south pole of the moon. Why? Well, because they want to understand whether moonquakes or the rumbles from asteroid impacts are going to be a hindrance to astronauts living long-term on the moon's surface at a lunar base. But the bonus that we get out of that is that we get a little bit more data on the inside of the moon. Again though, you'd ideally have many seismometers evenly distributed around the entire moon to test this properly, but there's no mission currently funded or planned to do that. The closest we've currently got is NASA's Lunar Magnetotelluric Sounder, or LMS, which was one of the 10 NASA payloads on the Blue Ghost mission, which landed in March 2025. It studied the electrical conductivity of the moon down to about 1,000 kilometers under its surface, which is sadly just shy of that mantle core boundary where there could be a liquid interior on the moon, which is around about 1,300 kilometers below the moon's surface. We've not had any results released from that mission just yet, but I'll keep an eye out for them, and when they do get released, I'll try and cover them on my channel, so make sure you subscribe so you don't miss out on that. And finally, the last item on my list there, what is going on at the moon's south pole? Remember NASA's GRAIL mission, which mapped out the pull of gravity from each part of the moon's surface? Well, it found that the south pole of the moon has a much stronger pull than other regions. But there wasn't like a visibly obvious reason why that should be. Like there's not a big whopping mountain there that's adding a lot more mass to give you a stronger pull in terms of gravity. In fact, the south pole of the moon stands out for the opposite reason. It is heavily cratered, way more so than the rest of the surface of the moon. It actually contains the largest structure on the moon, known as the South Pole Aitken Basin. It is 8 kilometers deep and spans roughly 2,500 kilometers in diameter, from the craters at the South Pole to the Aitken crater at the top, with a chain of mountains ringing the edge. It's not just one of the largest craters on the moon, it's one of the largest known craters in the solar system, and it's underneath that crater where the GRAIL mission found that the moon's gravity was stronger than it should be. The GRAIL data suggested there's something really dense beneath the moon's crust that's roughly 5 times the mass of Hawaii's entire Big Island. It's so dense, it's actually pulling the floor of the crater down by almost a kilometer. So what could this mystery density be? Now there's been a couple of ideas raised to explain this, but a lot of them hinge on the idea of a massive asteroid hitting the south pole of the moon around about 4 billion years ago. Now with an impact that size, most of the asteroid will have completely vaporized in the heat generated by the impact. But simulations have suggested an iron-rich core could have survived the collision and sank under the moon's crust, where it still remains today. Or another idea is that it's not just like a single lump under the surface, but if an asteroid did impact, it could have dredged up a load of the much denser material from inside of the moon that's now piled up there under the crater basin. Not like in one big lump, but sort of spread out. So to understand the South Pole Aitken Basin gravitational anomaly, that's really what we need to figure out next. Is it caused by one great big lump of something, or sort of like an overdensity that's spread over the region? So again, will Artemis help with this question? Because after all, the plan is to land astronauts at the South Pole and take samples of the surface from there and add a moonquake sensor there. Well, hopefully, yes, the rock samples that are taken at the South Pole should be able to tell us if an asteroid impacted there, and the seismometer will hopefully give us a little bit information about what's directly under the surface of the South Pole Basin. But again, ideally what you do to figure this out is to have a network of seismometers detecting moonquakes all around the moon so that you could detect how the moonquake waves actually behave around the South Pole Aitken Basin. Do they reflect off a harsh boundary of a solid lump of something? Or do they just get a little bit scattered because of an overdensity of material under there? Now, thankfully, there is a mission that hopes to do this. It is still in the planning stages. It's called the Lunar Geophysical Network, the LGN, that if funded would land on the moon in the 2030s. And the idea is that it would put 4 seismometers on the moon, spread out evenly across its surface, that operate for 6 years to detect asteroid impacts and moonquakes and map the moon's interior. But as of 2026, there's no confirmed funding for that mission just yet, anyway. So there you have it, 5 things that we still don't know about the moon and how we'd answer them. And some of you might have noticed that for every current or planned mission that I mentioned in this video, I also popped up the estimated cost of that mission. And there was a reason for that, but first a quick reminder that that money isn't just like, millions of dollars launched on a rocket into space, right? That money is spent on people and jobs and infrastructure here on Earth, and it does contribute to economies. So bear that in mind while we look at the total estimated costs for these 5 missions, which would be just over $2 billion. Compare that number though to the cost of the Artemis program so far at the end of 2025 of $93 billion. And that number is only going to keep going up and up and up with every successive mission. If you want even more context for that number, compare it to the cost of the James Webb Space Telescope, which is estimated to be just less than $10 billion over its 24-year lifetime. With those numbers, I'll let you make your own decision about whether the Artemis missions are worth the cost, at least for how much new science we'll learn. But perhaps the Artemis program will trigger renewed public interest in the moon so that future scientific missions do get funded. And hopefully Artemis will also have the same effect that the Apollo missions did in inspiring a huge wave of the next generation of scientists and engineers. But the fact remains that a lot of the outstanding mysteries that we still have about the moon are not solved by sending humans to one specific landing site. They are solved by targeted geophysics, by long-term monitoring, and by robotic exploration with careful sample return missions. Because although the moon is incredibly familiar to all of us, shining in our sky night after night, is still a world that we don't fully understand. And that, to me, is what makes the moon worth exploring. So if we want to answer this question of where the womb's water came from, that's a very different scientific question. But for now, transient lunar phenomena, oh my god, too many difficult words in one row. Still unexplained. And, oh, that was a weird squeak. I was trying to say and. To me, is what makes the womb. Why? Well, because they want to understand if mooncakes? Mooncakes. Oh. Making me hungry. Where was I? Oh, yeah.